Hello. Ankita, today also there is some problem.
I'm not sure. Let me check.
Oh, now I can see some noise. Okay. Yeah. Okay, I wasn't hearing anything. Okay. Okay. Oh, I see. Okay. Yeah. Okay. Yeah. Thanks. Hmm. 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 Hmm.
Good evening, everyone. Welcome to another session of Network Seminar Series hosted by the Center for Network Intelligence at the ECE and Administrative Service ISC. Today's talk is by Mr. Sushil Varma, and we will be speaking on dynamic pricing and matching for online marketplaces. Mr. Varma is a fifth-year PhD student in the Industrial and Systems Engineering Department at Georgia Tech, advised by Professor Sivateja Magunudi. His research interests include queuing theory, game theory, and revenue management with applications in online marketplaces like ride-hailing, load balancing, and stochastic processing or matching networks. Mr. Varma has won the Stephen S. Ravenberg Best Student Paper Award in IFIT Performance 2021. Before we move on to the talk, we'd like to request the online audience to keep your microphones on silent, except asking questions. And for questions, you can unmute yourself or raise your hand. Or type in the chat box with your questions. And for in-person audience, we have arranged for refreshments at the coffee shop. Please help yourself up to the talk. Over to you, Mr. Varma.
Thank you for that introduction. So welcome everyone. Thank you for being here and thank you for hosting me and IISc for this talk. So today I'll talk about a little bit of what I did during my PhD. So we'll talk about dynamic pricing, matching for online marketplaces like ride sharing and stuff. During the course of my PhD, I've met like several awesome people. I've been really fortunate. Popovic, she's currently at Amazon. She was a PhD student when we worked together on this. Among the professor at Tech, Francisco is at UCLA, the business school of UCLA, and Siva, who was here last week, is my advisor at Tech. So this work is motivated by new economy, which is online marketplaces, and there has been an accelerated rise of the economy in the past few years. For example, $204 billion revenue was generated only in 2018. On top of it, 36% of the workers in the US joined the economy in a way or the other. This has been corroborated by many different applications of the economy, like ride-hailing, meal delivery platforms, bread and breakfast, package delivery, freelancing, and many more. So with this, being a system operator, you would face mainly two challenges if you want to operate such kind of a system. The first one is a disparity of supply and demand. For example, if you have too many agents who want to buy something, but not too many agents supplying the same thing, then there is disparity in demand and supply, and you don't want to have that. And the second major challenge is misalignment of supply and demand, which basically means that if you have supply and demand, they are also equal to each other, but they are not compatible. That means the buyer doesn't want to buy when the seller is selling. So they're incompatible. So both of them will stay in the market and we won't be able to match them. So both of these are the fundamental problems, and we want to get over these issues. The first one is solved by pricing. So essentially, when there are too many demand agents, you might do surge pricing to reduce the number of demand agents in the future. And the second one will solve by smart matching. So we want to match these agents in such a way that these incompatible supply and demand pairs doesn't stay in the system. So because your current matchings will determine what your future agents are going to look like. So you want to match them in such a way that there are least number of incompatibilities in the system. So by doing dynamic pricing and matching smartly, you can get over. Now what we do is we take a stochastic network viewpoint, which is a stylized model, and it has mainly three ingredients. The first one is the type. So as you can see here, there are different types of agents or different. The terminology I use is customers and servers. So there are different types of customer and different types of servers. So for example, in a ride-hailing system, you can think of it as the location, and if a customer wants premium ride or a normal ride, can be a type of the customer, and similarly the type of the server. Then the second feature is compatibility. So there is not a full compatibility, but a partial compatibility between this customer and servers. That means if you are too far away, then you might not want to match someone who's asking for a ride at the airport, and if the driver is here, you don't want to match them.
So this compatibility means you have the supply and demand, but this thing, I mean, due to some reason, you cannot service.
Correct.
You can give the service, right?
Exactly. So for example, if there are, so these are types. So if there are these types of customers waiting in the system, and these types of servers also waiting in the system, you cannot match them because they are not compatible. So this is exactly this misalignment of system. And the third feature is match. So essentially, if you have compatible customer and server, then you can decide to match them with each other, and as soon as you match them, they depart from the system instantly. Now, under this kind of a stylized model, the question we are asking is that we want to set prices and perform matchings in such a way that our profit is maximized and the delay experienced by the customers and servers are minimized. Because delay is also important because we want to give them a good experience while making sure that the platform makes a lot of profit.
So,
Yes.
when you mention delay, is it the matching delay or the service delay?
The delay will be the amount. All I'm going to use is the Q length. So it's essentially the amount of time the customer and the servers are going to spend in the system in steady state.
And what do you mean by the Q length?
Q length as in, so there are different types of customers and servers. So we'll come to that exactly what I mean. But essentially, these types can come, and so there's going to be queue for each type. They arrive in the system, and then they can come and wait in the system. So then that will give you the number of customers that are waiting in the system at any point of time for each time. That's the queue length. That's the state of the system.
Okay. And the customer departs the queue after being matched, or
Instantaneously, yes. So as long as, for example, if this customer and this server are waiting in the system, then you can decide to match them with each other, and then this pair depart from the system. But for some reason, you may also decide to not match them, or for example, if these pair is waiting in the system, you cannot match them at all. So then they'll have to wait in the system. So at any snapshot of the system, you might see some customers of each type, some servers of each type waiting. And by delay, the proxy I'm going to use is just the sum of the lengths. So we want to keep if the queue lengths are small, then essentially the customers are getting matched first.
one more question.
Yes.
Are the prices set by the service provider or by the system or the platform?
What's the difference? So basically there's a central operator who's going to set price for all the types of customer and server, and also decide which pairs to match.
Okay, so the say in this case, cab driver can't set the price.
No,
it's the
driver can-
operator.
Correct, exactly. Yeah. So driver can decide to either join the system or leave the system. They can see the price and decide to join or leave. That's the only decision they can make. But the prices are set by the system operator. So drivers don't have any say in what prices, which is the reality in some of these applications. Right? That you can see as a heat map of prices, but you can't set your own. I mean, there's some work on those lines as well, where they allow drivers to set their own private lane. And Uber has tried it in real life. It did not work because essentially there were a lot of cancellations. So it did not work very well. But that's another interesting direction there. Then there's a lot of game theory that is involved, and then you can analyze it. Yeah. We also analyze something like that, but a little different. What we do is what we say is the drivers can see all the prices, and then they can decide to join whatever cheaper. So that's some kind of a strategic behavior that you can introduce as well, where there's no full control of the price, but you can see a price vector, and then you can misreport your type and then join some other queue. You're this type, but you end up joining this type.
So what do you mean by type? Like how do you define?
Correct. So, for example, in ride hailing, the type can be the location of the driver. So then, by misreporting the type, all I mean is the driver relocates and goes to a different location and tries to get a ride, get a customer from that. Because you can see the heat map of prices, and then you can relocate to a different location and then try to get a ride from that. So in some sense. But that's some extension that I talked about at the end.
So each driver
yes.
can see every the prime record of every field.
Correct. No. So for this talk, I'm not gonna. That is just some extension that I just mentioned. I'll talk about it at the end if you have time. But yeah, very good.
For this, there is only one central operator.
Correct. One central operator. They're gonna set prices for all customers and all servers. All the server and customer can do is decide to join the system or leave the system. If they decide to join, then they are going to get the price that is posted by the system operator. And all of this will go through. So this was just an overview, but we go through all of these details. Thank you. Any more questions? Okay. Maybe what your question until I describe the model in more detail, but we can discuss it. So with that, just to give perspective, there are many applications that you can think of this stylized model. For example, again, we've been talking about ride hailing, so that's one example. And interestingly enough, you can have these kind of matching queues appear in many different applications, like payment channel networks, where there are bi-directional payment channels when if A wants to send money to B and B may want to send money to A. So that we can think of it as bi-directional queues. Again, I'm not going into details, but it shows up in many different applications. So studying systems like this can be of independent purposes. So this is stylized. But just for this talk, I'll just talk about ride hailing. Everything will be like the customer. But again, it's stylized. So let's start with like the simplest possible case that we can think of is one type of customer and one type. Now, the customer arrives with rate lambda and server arrives with rate mean. So the actual arrivals you can think of it as Poisson with rate lambda, Poisson with rate mean. Now, the first question that we might ask is where is the system state? So for people who might know queuing 101, that for a single server queue where there's no queue for the server, but just a single server waiting right there. Lambda less than mu is basically where the queue is state. That means the customer are coming at a smaller rate than the server can serve. But in this case, if lambda is less than mu, because there is a queue for servers, the server queue may blow up. So there may be a lot of servers that come in and wait in the system, and that makes the system run. Then you might say, okay, maybe let's make lambda greater than mu. But in that case, the customer queue is going to blow up because customers will queue up faster than the servers. And finally, the only case that remains is lambda equal to mu. Well, you might say this is probably like the best possible case here. But again, this is also not very well defined because the underlying Markov chain is just a symmetric random walk, and that is known to be null. This doesn't even scale very well because if you have a three-dimensional random walk, then it is transient. So this property doesn't even hold when you go higher dimensions. And what we want is a system, something that behaves better in a better form, like positive. So then the question is, how can we make the system? So we need some kind of external control because constant lambda and mu is not continuous. By having constant lambda and constant mu, you cannot be in the system. So one thing you can do is dynamic pricing, which essentially by pricing I mean you can make these arrival rates as a function of queue length, which means the system operator is going to look at the queue length, which is just the number of customers in the system, number of servers in the system, and then based on that, it will set a price for the customer and a price for the servers. And based on the price, the arrival rates of the customer and server is different. Because if you set too high price for the customer, the arrival rate will be lower and vice versa. So that's essentially dynamic pricing, where prices are set based on the queue length and the arrival rates are the product. Now, with that, you can, for example, if the customer queue is too large, you can reduce lambda, and similarly, when server queue is too large, you can reduce mu. Yes.
So how do you calculate the dynamic pricing? Is there any algorithm?
Correct. So that's something that system operator can model design. So that's the first question that we are asking, that what are good dynamic pricing policies. So that's a decision maybe that you can design. Right. So again, by the end of the talk, you will see some examples of good dynamic pricing policies that work well based on the objective that we are asking. Okay.
Just one question. So here the mu that you modeled, so it's an arrival, but the number in the queue, server queue will be bounded, right? Like it's like usually it's the number of servers that is constant, and they are serving at different service rates, right?
Correct. So that's more classical view, but here essentially what I'm saying is there's no distinction between customer and servers per se. There's just a queue of servers and they keep arriving with the rate mu. So rather than the servers serving with the rate mu, they're arriving with the rate mu. So if you use one, then one customer arrives for one server arrives per unit time, and the queue can just blow up because there's no there's no capacity constraint there. Like it's not like classical servers where they are just sitting and serving the customers, but they come in and queue up. So this queue can even go to infinity.
So how realistic is that in assumption of infinity?
Right. I mean, so by that I mean essentially you want a system that behaves well. Like going to infinity essentially means that you will have long renewal cycles. Like the time to come back will be really large, and you might go really far away. So you might see snapshots of the system when it is highly unstable. When you don't have any external control, you might see a highly unstable system at a snapshot. If you think of this a taxi stand where two cars are coming per unit time, but only one customer, then you might see snapshots of the system. Even if this happens for 1 hour, then you might see a lot of drivers just queuing up and not a lot of customers if you don't do any dynamic pricing. And that's kind of the product of the system being unstable. That's how we are quantifying. Like we don't want things like that. And in some sense, stability is going to help you. Essentially, it's like a zero order condition that that you don't. If you keep running the system in steady state, you don't want things to go to infinity. That's like the zero order condition that my system to hold. But again, that's again a choice of analysis. You can again say that okay, even if my system is unstable, I only care about a finite time analysis, and I want a system to perform well for a given time horizon. Then for that, I don't care about stability because nothing will go to infinity in a finite time. Then in that case, you might have your objective function, which is more transient than steady state, and then you don't care about stability at all, and then you might want to design your policies which doesn't really take into account.
So are you going to define stability formally?
Correct. So stability is essentially positive recurrence of the underlying market. So here, because lambda, the customer arrives with Poisson lambda and Poisson mu, the underlying Markov chain here will be just a random walk on integers from -infinity to infinity, and that becomes a Markov chain. And then what I am interested in is that underlying Markov chain is which by that I mean the underlying Markov chain is positive. And by positive,
I mean, the state is sum of these two things?
Right. So that's a good question again. For this very special case, it doesn't really make sense for both the customer and server to communicate in the system. So in this case, you might just match all the customer and server that are waiting in the system, and the only thing that you might be interested in is the imbalance, which is the number of customers minus number of servers, and under that case, the underlying Markov chain is just a random. Because it will jump up with rate lambda and jump down. So it's a sequence. And even in the most general case, you can come up with a CPMC, and then that will be a CPMC that will depend explicitly on your pricing and matching policy. But it will still be a CPMC, and then you want your policies in such a way that you have positive, which is the will come back. If you start from any state, you will come back to that state probability 1, and the expectation, the time to come back, the expectation is 10. It's less than. So that is the definition of positive recurrence essentially, and what positive recurrence gives you, along with irreducible and aperiodicity, is that there exists a steady state, and the steady state is unique. Then, if there exists a steady state and it is unique, then you can essentially care about, if I care about the performance of system in the long term, then all I care about is how the state is. So a pricing and a matching policy will induce a steady state distribution, and all I worry about is the objective, the expectation of the objective under this state. And this will be, I'll make it a little bit more precise. Does that kind of make sense? Okay.
I'll hold my questions.
Yes. Cool. So again, just a quick snapshot of the literature. So there's a lots and lots of work, very recent work on things related to matching queues. So there are actually many different models of matching queues, and as I was mentioning, some people care about steady state, some people care about transients, and the underlying assumptions are really different, and that essentially leads to many different models, but relevant, similar but different models, and there are different technical parameters in each one. The thing that is different for our case is most of the models where system is inherently unstable, because if you don't have external control, you don't have stability. Only transient analysis has been done, except in a few papers, but essentially we do a more fine-tuned analysis. But again, I'm not going to the details of exactly what the differences are. So with that, just a quick overview of what we talk about. I mean, I like that we are getting a lot of questions. Very nice. So maybe we'll not finish the whole thing, and that's completely fine. We'll go until how much ever we can. But question for me. So the talk is mainly divided into two parts. The first part is based on this paper, where essentially what we provide is a near optimal pricing and matching policy, near optimal in some asymptotic sense, with some rate of convergence properties to again some fluid upper bound. So again, there are a lot of things here that are unclear, but I just wanted to give an overview of what's coming up. So what you can get out of this is near optimal pricing and matching policy, because that's the main question that we ask. That under such kind of a stochastic matching network, can we come up with a policy, pricing and matching policy that gives you in terms of profit and dividend. So that's what we'll answer first. And the second part is based on this paper, where essentially here we are worried about expectations under steady state, but here we look at the complete distribution under steady state of the queue, and we'll show some interesting phase transitions for the limiting distribution of the queue line, which is not like classical queue. So there's something interesting going on here. Again, this is also very vague, so just giving a very high level overview of this. So let's start with this, and from now on, I'll try to make everything very precise. And if there's any question, please ask. So again, the model is stochastic matching network, and it's a continuous time model. Essentially, what happens is first the system operator is going to set prices for each type of customer and server. So sets the prices, which determines the arrival rate. Next, once you know the arrival rates, then the arrivals happen in the system, which is based on Poisson process with the prescribed arrival rates. And finally, after the arrivals happen in the system, then the system operator can do service, which is basically matches certain pairs of compatible customer and server. You may even decide to not match a compatible customer and server, and that's completely fine as well. That's again depends on the system operator, can come up with whatever policy. And this continues essentially, and under this kind of flow of decisions, you get a continuous time. Yes.
So, for example, in that you have connected to one customer and one service. So, do they have that power to reject? What
No.
they have done?
Yes, correct. Again, that's a very good question. So that is not considered. Whatever system operator decides for matching, they have to follow. The customer and server. But again, that's another interesting.
That's the condition for establishing stability, right?
I mean, not really. You can analyze systems where you give freedom to customer and server where they can reject rights and stuff. But again, you are adding more strategic behaviors, then you might want to design your policies in such a way that you still get stability. So, I mean, you can always get stability, right? You can just jack up the prices so much that nobody joins the system and then it's always stability. You can always get stability. That's not a problem. But then the problem is with stability, you want to have good performance as well. But again, that's a question where you are extending the model where you have stability. And again, that's also very good.
So, how do you define compatibility in this?
Correct. So this is given to you. So this bipartite graph is given to you. Each vertex of the bipartite graph is you, where you will have certain number of customers waiting at any point of time. So the state of your system is just going to be the queue lengths at each queue. So the number of customers of this type, this type, this type, this type, and number of servers of this type, this type, this type, this type. So that's the state of the system. This compatibility graph is also given to you. So this completely determines the state. And then given the state and the compatibility, you will decide the prices and so on. So it's a system primitive.
So the compatible set is a subset of the
Complete graph. Correct. And that can be, so right now we are not imposing any assumptions on the analysis goes through for the first part of the analysis goes through for any compatibility graph that you give me. But later we impose some assumptions for compatibility. But for now, this can be anything arbitrary. It's a fixed, incomplete bipartite graph. It can be complete as well, and that's just a system primitive. Any more questions here? Good. Good. So it's a CTMC. Now under the CTMC, we want to analyze this objective. So again, I'm making the profit minus delay more precise here. So we want to maximize the expectation when the expectation is under steady state. That means if you don't have stability, this expectation doesn't even exist. Now under this expectation, we want to maximize this quantity. It has three parts. The first one is the revenue. So revenue essentially is price and quantity. What is the price? What is the quantity? Is just the arrival rate. Is the quantity. And what is the price? It's determined by this inverse demand curve. So it's a one-to-one mapping between price and quantity. So depending on what price you set, you will get an arrival rate. And F is just the inverse of it. So given a quantity, it will tell you what price you set to get that quantity. So F of lambda is just going to be the price that you set for J type of customer. So this is the revenue that you get from J type of customer. When you sum over all types of customer, you get the total revenue. Similarly, the total cost. This is the inverse supply curve. Now this is increasing because if you want to increase the quantity, you will have to increase the price that you offer to the servers, because servers you are giving away money, you want to give more money if you want more arrival rate. So that's why this is increasing, and this is a increasing function. And finally, there is a weighting penalty, which is just this weighted sum of queue lengths, where S is weights, which is peaks. So weighted sum of queue lengths, where queue length includes the queues of the customer and the queues of this. So you want this to be large and this to be small. Under the constraint that you have feasible matching, that means you don't match any incompatible customer and server, and you have a stable system. Because if you don't have stability, then this is an ill-defined. But again, if you don't want to look at stable systems, you can again change your objective and work with stable systems. Alright, so this looks like a complicated kind of objective because you have arrival rates which depend on freelance, lots of things are multiplied with each other. There's expectation under steady state, which is induced by a pricing and matching policy, so you don't know exactly what the steady state distribution is going to be for a given pricing and matching policy. So it's a pretty hard objective to build. And when something like this happens, what we do is we change our. So that's what we do. We come up with a fluid model, which is by replacing all stochastic quantities by their deterministic counterparts. And what I mean by that is lambda j of q is just replaced by constant lambda j, which can be thought of as expectation of lambda j of q. So this is the revenue part, this is the cost part. So you have revenue minus cost here, and here I've gotten rid of the q length completely because it's a fluid model. So you can think of as fluid flowing, and there will be q lengths under the fluid model. So for that you can think of this diagram essentially that fluid is flowing from this direction, and then you want to route these fluids from these pipes to these pipes, and then this fluid keeps flowing. So there's nothing that gets clogged. So there's a fluid. Is this fluid flowing from that? And to make sure that there is no clogging, essentially, you want to do rate balance. That means this plus this should be equal to that, and this should be equal to this, and this plus this should be equal to that. So this is essentially the balance equation, where chi ij can be thought of as the rate of I type of server matched with j type of server. And if you sum over all the types of servers, then you should get the arrival rate of it. And similarly for the servers. And again, you have compatibility constraint, which means that you cannot match any incompatible customers. So that's where the compatibility graph plays a role, where if the edge is not in the compatibility graph, then you cannot match them at all. That means the rate of matching. So all of this is in the fluid sense, where everything is boiled down to rates. And now this is a very tractable optimization problem, because under certain assumptions, this is a convex function and these are just integers. So very, very easy to solve. You can readily solve it, but the question is, how does this give you any information about the previous one? Because that's what we care about. This is just something that we do. So that's what we first make precise. Essentially, what we say is this fluid model, provides an upper bound on the achievable profit under any pricing environment. So this is kind of the best case scenario. And the intuition is that these are some prerequisite constraints for stability, because even if you don't even have a rate balance for a single queue, it's just lambda equal to q in steady state. If you don't even have rate balance, then it's hopeless. You cannot really make the system stable. So these are necessary but not sufficient conditions. And again, by density equality, this can be thought of as an upper bound on your previous objective function, because if you take expectation inside, if it's a convex function, then density equality gives you what you need. So with that, this essentially gives you an upper bound. So that's good, right? Because now you have a benchmark. And then the next question you will ask is, can I achieve it again? So any guesses? So essentially what I mean by achieving the benchmark is, can you come up with pricing and matching policy for your original system such that the objective function that you get is same as the fluid objective. Correct. So is it a hard upper bound, or can you actually just give me a pricing and matching policy and that gives you this upper bound? If that is possible, then that's it, right? All of us can go home because we have another. Correct. Yeah. Good point. Nice. So essentially here I very nicely removed the Q length here because there's no Q length in the fluid model, and that plays a part because you can possibly get the best out of this, but you may lose out because of the Q length. So you cannot achieve this upper bound, but then again, you want to be close to it. So then the next question we ask is, can you achieve it in a certain asymptotic regime? And that's what the talk is. So we define an asymptotic regime and ensure that under the asymptotic regime, you can propose policies that gets arbitrarily close to the So the regime we consider is, we consider a sequence of stochastic systems which was the previous CTMC sequence of them, where you scale the arrival width by a factor theta and analyze the system as eta goes to infinity. So this is a large scale regime where more and more customers and more servers are coming for unit. And that kind of helps you to make things practical. Now, under this large scale regime, you define a profit loss, which is again how much are you losing from the benchmark. Where your benchmark is the fluid profit, is gamma star, but you want this to be very small compared to the actual upper bound, which is beta gamma star. That means if this is sublinear in beta, then you're good, because as beta goes to infinity, this upper bound is of the order beta, but the thing that you're doing is sublinear order of beta. That means you're close to zero, and that's the definition of here. Any questions here? So essentially, what I did was we have a stochastic system, and then I changed my objective and came up with a deterministic system, which is a fluid model, and that gives you an upper bound. And then now I want to get as close to the upper bound. All right, so let's get to the first result. So here I'll define two pricing policies and show that all combinations of them, that is 4 combinations, all of them are actually near optimal in this. So the first one is static price. Simply, essentially what you're doing is you are setting a constant price until a threshold top, and after the threshold you are setting a very high price. That means nobody can enter the system after that. So it's just a static price, but cut off after a point, and this cutoff is going to ensure stability. This lambda star j is essentially the arrival rate prescribed by the fluid model. So the intuition is you want to be as close to the fluid model as possible, but you want to still ensure that your Q-max are, and this buffer is ensuring. The second policy we use is the two-price policy, which is just the generalization of static price, where you have this one parameter here. Here you have a second parameter, where after a threshold you reduce the arrival rate by a factor epsilon, rather than just letting it go to 0. So those are the two pricing policies. Two matching policies also. The first one is random matching. So essentially, this random matching is going to mimic what the fluid model is doing. So the fluid model says the rate of matching of I type of server to J type of customer is chi star ij. So I will match any arriving server I to J type of customer with probability proportional to chi star. If chi star ij is more, then I want to match more and more servers to that type. So then this is kind of mimicking the optimal solution.
This is still within the compatibility set.
Correct. So a chi star ij will be 0 if ij is not in the compatibility set. That means you will never match incompatible customers, because the probability of matching is lastly, next policy that we consider is max rate, where now max rate says that okay, I don't care about what the fluid model is saying. I'm going to do something that is intuitive and sensitive. So what it does is, if an I type of server arrives into the system, it's going to look at all the compatible customer queues, and it will match it to the customer which have the most number of customers waiting. So because you want to bring the system close to 0, and essentially if there are too many customers at the time, you want to reduce that more and more. And that's what match rate is doing, is matching to the customer type which has the largest queue. And vice versa. If the customer arrives, then it will look at all the compatible servers and match it to the queue that has the most number of servers. So that's max rate. Now we can analyze static plus random first. You want to
in the static price thing. That QG is the fluid thing.
no, so right. So this is not in the fluid. This is the actual queue length of J type of customer in this stochastic.
Isn't it that automatically establishes?
Correct. This will establish the
One constant is
correct. Yeah. Now, but you again, stability is very easy to satisfy, right? Just don't allow anybody. That's stable. So that's like something that's a technical issue, but again, very easy to get over it. But the major problem is to make the profit loss model as well, and this is what these boxes are going to say. So essentially, when you do static plus any matching policy, profit loss is square root of theta, which is again near optimal because your upper bound stays as order theta, so the loss is sublinear, so that is near optimal. But if you go from static to two price, you would expect that we get a better profit loss because this is a generalization with static policy. And that's essentially what you see, that this improves from square root to cube root, and cube root is smaller. So a natural question somebody would ask is, can you improve this even further? Can you improve this from cube root of theta to something like this? And the answer to that is no. We also do lower bound that under a large class of pricing policies and any matching policy, you cannot beat this. That means, so let's see a few takeaways from this theorem. The first one is that dynamic pricing is better. So two pricing is better than static. The second one is just a small amount of dynamic component is enough because that gives you near optimal profit, at least in terms of what I've defined as my objective. So this small amount of dynamic component gives you all the benefits of dynamic pricing. And finally, the optimal profit through prices, the pricing policy is the primary driver because whatever matching policy you use, it really doesn't matter. You still get it. Where random is something more naive because it doesn't really look at the actual equivalence, it's just trying to mimic the fluid model, but it still gives you a very good profit. But then coming up is the advantage of match rate in some in terms of something else. That's what's coming up. But before that, so I think we'll just finish first part and then talk about so the intuition. So before talking about that, let's look at the intuition of where this cube root is coming, because square root you might have seen a lot of times because that's like central limit theorem. You always see eta scaling is like fluid scaling, and then you get a fluctuations around it, which is order square root of eta again. That's just a very high level comparison with what we see in law of large number as central limit theorem. But cube root is something which you don't see as much. So here I'm trying to give some intuition of why you see that. So here I've just written the profit loss by writing all the terms. So this is the fluid profit. This is essentially the revenue loss. So the fluid profit minus the profit that you get under your pricing and marketing policy, and you have some of expected. Now under that, consider a general pricing policy which is an silent perturbation of the fluid policy because you want to be close to the fluid, but you can move a little bit up and below fluid. So it's a dynamic policy, but you can only go plus minus epsilon to fluid. Under that, you can think of this loss of profit as you are operating at x star plus some epsilon. X star is the optimal. Then you can just do Taylor series. So again, Taylor series will be eta epsilon square and so on. The first order term will disappear because of the optimality of x star, because x star is optimal in fluid. So what you get is beta epsilon square, which is the revenue loss. And for expected Q length, you can think of it like a single server key in heavy traffic, because single server key in heavy traffic, essentially you have a drift towards zero, which is of the order service minus the arrival rate, which is similar to the parameter epsilon here, because epsilon is also characterizing the drift towards zero. So in space they are very similar. Like in T-man bound, you know that the expected equivalence is of the order 100. So here there is a clear trade-off between the revenue loss and expected equivalence. And then we can optimize this trade-off by carefully picking the right value of epsilon, which is again equate these two together to get epsilon beta power minus 1/3 to the profit loss. And that's the intuition for both upper and lower bound. And you can make this a little bit more precise by not considering any asymptotic regime, but let's say you want to define pricing and matching policies such that expected Q length can be at max this much. So given a delta, you want to make sure your expected Q length is at most 1 over delta. Then we can show that the best profit that you can get is order delta square less than the optimum. So this trade-off is something more fundamental. You don't really just see in the asymptotic ranking, but you see it in general because this is the asymptotic result. And to test this max weight achieve this trade-off. So that's good. So that's the solution for eta per 1. Now I'll just finish with why max weight is better than random because that's what we expect. So let's start with, so essentially I want to characterize the dependence on n as well, where n is the number of types of customer server, because all I cared about was eta, which is the rate at which the rates were increasing, because it was a large scale regime. But here I'm also interested in, if you have a large market, then how does your profit loss? So let's start with two simple examples. So the first one, let's say you have copies of these simplest case, which is single server queues, single link two-sided queues, and n of them. So then what would be the profit? So we know for one it is eta per 1, then what would be the profit loss for this? This is where you have n of them.
Will scale with the number of queues?
Correct. Yeah, essentially, because these are just independent, they don't really interact with each other. The profit loss is just an independent matching queue. The profit loss will be for each one is eta per 1/3, and there are n of them, so n eta per 1. Now, let's see the other extreme where everybody is connected to everybody. Now, in this case, what do you think the profit will be in terms of n? So the best case scenario would be it doesn't scale with n at all. That's the best case scenario. But would you expect something like that? I'll give you a hint. Think of it as a one resource pool matching queue, because it really doesn't matter what type you are, because you can match anybody with anybody. So you can think of it as one giant single link matching queue with arrival rate n times.
Right.
So then what would be the profit?
No, they need to do the one.
Correct, exactly. Because when your arrival rates are scaled by eta per 1/3, this can be thought of as arrival rate scaled by n times eta. So the profit loss you will see eta per 1/3 n per. So here you see there is a large spectrum of what you can see the dependence on n, and this is again independent of what mapping policy you use, because whatever you do, it has to be n here, and whatever you do, I mean, if you do a good pricing policy here, you would see n per 1. So again, it depends on the inherent structure of the graph that I give you. So then the objective is first we want to come up with conditions on the graph such that it behaves like a complete graph. So it can be much sparser, but it still behaves like a complete graph. And the second thing is we want a policy that achieves resource pooling. Again, further develop, Max will do that for you. So the condition such that it behaves like a complete graph is famously known as CRP conditions. Again, not going to go into the details, but it's similar to Hall's condition on weighted graph. Again, Hall's condition on unweighted graph is very similar to just connectivity. So here you want, in some sense, connectivity, which is like the least requirement. Because if you see here, things that are not connected, there are problems. So you at least want connectivity, and that's what this is kind of proposing. So the above implies the graph is connected, and then again it implies something a little bit more, which again relates to stability region and integrity. Again, we'll not go into the details of that. So now we'll consider the case where you are given bipartite graph which satisfies the condition. So the compatibility graph and the arrival and the fluid solution is in such a way that this is satisfied. So now we want to augment these results so that it depends on n as well. So we want to augment and add how it depends on n as well. So first we show that for random it can be as worse as n, whatever you do. And for max weight, again for this it's square root of n, good, but not the best. But if you do two price, then you get n per 1. And from our previous discussion, we know that you cannot go beyond eta per 1 and n per 1, because even for complete graph you cannot do it. So here you can see optimal performance in terms of beta in terms of n and a clear distinction between random and max weight. So again, three takeaways. Max weight is better than random. It is better in terms of the number of types, so it behaves much better when you have a large system. And you can see that it's really better. Second is max weight is optimal with respect to n, because here you see 2 price plus max weight together gives you n power 1/3, eta power 1/3. So max weight is something that can give you the best possible profit with respect to n and eta. And finally, something a little bit more subtle is that you need to have the right matching policy along with the right pricing policy to get the best of the both. Because if you have the right matching policy but the wrong pricing policy, then you are suboptimal in terms of both. Similarly, if you have the right pricing but wrong matching, you are optimal here but suboptimal here. So you need to have both of them together. A joint optimization is required to get the best. And with that, essentially we are able to set prices and perform mapping that maximizes profit and minimizes the growth. If I still have 10 minutes, 10 minutes. Is that 10 minutes?
Yes, 10 minutes.
I'll take 5 minutes. So I'll just give you an overview of what other things you can do here, because again, there's a lot of interesting questions about what can you do with the model, you can add something, so and many things you can do. So the first thing we did was we analyzed. So till now we are talking about expectations of event. Even before that, any question on everything we talked about?
So if you please go to the back.
Yeah, for sure. Yeah.
No, where you have kept this, like, eta power 1/3 and then n power 1/3 you have taken this.
The two examples.
Yes.
Yes.
So you have told that we will take all the Q as one, and so this was the control like that.
Correct.
So are there any assumptions doing that? Can we take just like that?
Right. So intuitively we think it doesn't really matter because all the types are homogeneous. So again, there is no incentive in waiting in keeping customer and service both waiting in the system. There's no incentive to do that at all, because the only incentive to keep compatible customer and server waiting in the system is that maybe in the future you have better matches. And maybe you can match more than you could have done if you have already matched the compatibility. But here it really doesn't matter because everybody is compatible with everybody. So you have absolutely no incentive in keeping both customer and server waiting. So your matching policy will be the optimal matching policy will be such that it greedily matches. If you have compatible, it greedily matches. Now with that, your system, the state of the system boils down to the imbalance. Again, which is just the sum of events minus sum of customers minus sum of servers. And you can now under any pricing policy that only depends on this sum of customer minus sum of server, you cannot beat that. Is the result that we are seeing. So there are again some underlying assumptions, but again, if you think intuitively matching, the greedy is best. That's the first condition, and then once you show greedy is best, then essentially all you care about is the imbalance, and it again goes to.
In this formulation, the delay is captured by the tool.
Correct. Yes.
There is no other measure of the tool.
Correct. In this measure of the delay.
Yeah.
Yeah. So again, yeah, that's a very good and very recurring question in field theory where people ask, can you characterize the delay rather than the field end? And I think characterizing delay itself is much harder than actually working with the field end. So essentially, it always boils down to working with field ends as a proxy for the delay. Some justification is Newton's law. The expected waiting time will be equal to expected field end times the trial rate or divided by. So Newton's law would give you, if you know the expected field end, then you know the expected field end. So in expectations, it really doesn't matter. You can go from one to the other.
Yeah, the only thing is if you are talking about the steady state expectation, right?
Correct. Yeah, exactly. Yeah. If you move away from expectation of steady state, then none of this will work. So then this is not interchangeable. Then working with waiting times and working with coolant will become good. Because there's a lot of work that characterizes the whole complete distribution of the coolant in steady state, but not many work that actually gives you the complete distribution of the waiting time, because I think it's not possible to do that. But yes, in steady state, it's interesting.
And I don't know whether you already shared. So you mentioned positive recurrence. So that again doesn't guarantee that it's a very loose kind of condition. Whereas your delays can go to much higher value.
Correct. And that's why the objective has minus Q length term that takes care of that. That you want to have a high profit, but you cannot have a very high Q length.
So how do you set up? Is there a way to make it better by setting some tighter bounds?
Right. So that's what this intuition I was trying to show here, was that there is an inherent trade-off between these two things, that you can get arbitrarily close to your fluid profit by making epsilon arbitrarily small. But because of that, you can expect your coolant to just blow up, because essentially what you are doing is you are getting rid of this external control. So epsilon can be thought of as this external control. And when you let epsilon go to 0, that means your external control is vanishing. And when your external control is vanishing, that means you are reaching closer and closer to null rectangles. Right? Because if epsilon is going to 0, that means all your arrival rates are becoming constant. Under constant arrival rates, we've seen that it is either transient or not. So you are reaching closer and closer to null reckoning. And something very similar happens in a single circuit, where when the arrival approaches capacity, then essentially you are approaching null reckoning. And that's why you would expect your coolant to blow up, because you are approaching null reckoning. So you can get arbitrarily close to the profit, but your coolants are not going to blow up. Now, if your objective is linear again, in such a way that you only care about expected coolant and the profit loss, then your trade-offs is just going to look like this: eta epsilon square and 1 over epsilon. And then in that case, you would pick your epsilon that optimizes this trade-off, because very small will make this very large, but very large will make this very large. So there is an optimal value of epsilon, which is just. So this is kind of getting best of the both worlds. If you try to make this 0 to be low, then this 0 will be low. And this kind of gives you something that's the best trade-off. Yeah, and that's why this is something that's fundamental that we will see in systems like this, where you will see an interplay between profit and coolants, which again makes sense, because you can get a very high profit if your customer and servers are very delay insensitive. So you can just make them wait for a very long time and then make a lot of money. And that's what we see.
So in your policy, this case will come into picture?
Right. So it doesn't actually, because everything is asymptotic here. So all we care about is the orders of theta. So I mean, all you can do is take this as out. And that's it. It really doesn't matter. You can have this sum of coolants, and it's the same thing in terms of asymptotics. But if you want something that works well for pre-asymptotics, then you might want to consider this S and make your epsilons different for different Qs, and then give more priority to. I mean, we make epsilon a little bigger for the Qs that have higher weights. Yeah.
So basically, you can have SIQI for a particular Q.
Correct. Right. Yeah. You're right. So yeah, for asymptotics, it will be a lot of things here too. And that's why asymptotics help you. But it also gives you intuitions like this, because you can't get intuitions like this without anything else. That's hard. So I guess just to conclude, 2 minutes. That's it. So you can do many things with it. Till now we were just talking about expectation, but I can ask a question where you want the entire stationary distribution of the equivalent and not just the mean. So that's a much harder question because you want much more all the movements, for example. So we start with a very simple case. In this very simple case, the takeaway is that under these similar asymptotic regimes that we talked about, we can characterize the stationary distribution, and something that is interesting is you see phase transition. So there were two parameters, epsilon and tau, and depending on the asymptotic regime being epsilon going to 0 and tau going to infinity, which means again you are approaching the accuracy. So you are managing the control. That can happen in two ways, where either epsilon go to 0 or tau go to infinity. Now, because there are two parameters that are varying, you want the relative rate in which they are going to their asymptotes, and that gives you three cases where epsilon is dominant or tau is dominant. For example, here epsilon is going to 0, but tau is a constant, and here epsilon is a constant, but tau is going to infinity. And under these three cases, we see a nice phase distribution. So you see in this case it's a Laplace distribution, which is very similar to classical bipartite. Here you see a uniform distribution, which is again interesting because we don't generally see uniform distribution in stationary distribution. And again, the cutest part I think is that in the middle regime where it's going to a constant, so they are comparable against each other. You get a nice hybrid distribution. So a Laplace case stitched to the uniform. And this can be extended to again very general arrival rates and very general arrival distributions as well. And then you can get, I mean, the Laplace and uniform stay the same, but this generalizes to a Gibbs distribution, which again depends on exactly how your arrival rates, exactly your pricing policies. So by this, we are able to characterize the complete distribution of the two lengths for the simplest case of the single, right? Under certainty. Then other works on matching views that we have is again incorporating strategic server. So the server strategy is like that. Is what if a server arrives, sees the prices for all queues, and then says what if I lag and join the queue. Then the server may say, okay, the price of this queue is much higher, so I can report my type, go and join this queue and get higher rewards. Under this setup, we have incentive compatible near optimal pricing and matching policy, because now you have strategic agents, you have to worry about incentive compatibility or match equilibrium. So your pricing and matching policy should basically ensure that you are operating in equilibrium and still ensure that you have near optimal price, near optimal in terms of so that's one extension that you can have. And another line of work in the space of this matching queues is again you can think of as a spatial queue where the customer arrives uniformly at random in the space and your server are distributed uniformly at random in the space as well. And then here now you are doing spatial matching where if a customer arrives here, then we have to decide which server to essentially send to pick up the customer. So this becomes a spatial model. And this we consider this for electric vehicles, and the question that we are trying to answer is for a given arrival rate of customer, how many electric vehicles and chargers do we need to achieve a desired service level? So that's again a canonical question that we would ask in such a model. And then the results are essentially the Pareto frontier, which characterizes the trade-off between. So, for example, if you have a lot more chargers, then you might need a little bit less fleet size. And if you have lots of fleet size, then you need a little bit less chargers to satisfy a given service level. So we characterize the trade-off. And the second one is the question is that once the customer arrives, which server as in which car to dispatch to pick up that customer, and we propose near optimal dispatch policy that determines the EV that will pick up an arrival. Those are the two takeaways from the side of work. So essentially, here what I'm trying to say is there are many things that you can do in the space of matching queues, where there are many different models, many interesting questions and applications. And some of the questions you guys also pointed out during the talk that you can have many extensions that can be very interesting to analyze. And a lot of people are working on it. So I think thank you for listening. Question?
Any questions?
Online questions.
You can see that this man.
Okay. Thank you, Sushil,
Thank you.
for an informative talk, and we shall go for refreshments.
Nice.
Thank you.